The sun is a center of atomic activity. Within it, atoms of hydrogen continually combine, forming larger atoms of helium. This reaction releases energy, some as prominences and flares we can see through the telescope, and some as invisible energy waves that move out into space. Despite the fact that energy is moving through it, space remains dark. The energy moves in small amounts, each known as a quantum. Quanta of energy move out from the sun in every direction, including that of our planet, the Earth. But the Earth is just a temporary stopping place for energy. Eventually, it is returned to space. Our story is about what happens to energy on Earth between the times when it strikes our planet and it is returned to space. Energy from the sun that reaches Earth may be thought of as activation energy. It activates or speeds a great number of reactions. For example, when activation energy strikes snow on a mountain, the snow may melt. The energy changes solid snow crystals to a liquid, water. The water trickles down the mountainside, forming an ever-growing stream. Where is the energy now? It's no longer the energy of sunlight, and it's not activation energy. It has been changed to the energy of movement. Here, too, the sun's energy is being changed, but not to movement that we can see. The cliff contains iron that has rusted, and the rusting has been speeded up by activation energy from the sun. You see, rust is iron oxide, a combination of atoms of iron and atoms of oxygen from the air. These symbols represent only a few of the millions of atoms there are. The atoms are constantly moving, and they tend to join each other, forming rust. As this happens, the sun's energy may warm the atoms of oxygen and iron. The warmer the atoms become, the faster they move, and the quicker they combine. Where is the energy now? It's no longer activation energy or the energy of sunlight. Some holds the atoms of iron and oxygen together, and some is given off as heat. The heat of rusting iron, scientists find, is not just heat reflected from the sun. There is some additional heat as well. Rusting and other chemical reactions that release heat are known as energy-giving reactions. Do all reactions on Earth give off energy? To find out, we might follow a train of iron ore until it arrives at a steel mill. There, iron oxide is changed back to iron by heating the ore along with gas. To understand how this happens, look once again at iron ore, rust. And remember that rust is a combination of iron and oxygen. The gas that's brought in contains hydrogen atoms. Two atoms of hydrogen combine with an atom of oxygen, forming water that evaporates. Unlike rusting, which gave off heat, this reaction requires heat. It is known as an energy-taking reaction. We've seen that men making steel use energy to activate certain changes. Similarly, we've seen that the energy of the sun activates natural changes on Earth. Men may put energy to use on a much smaller scale, for example, using fire to warm the air or to cook food. Looking at a fire, a scientist knows that even this energy has, in a way, come from the sun. The wood and coal that we use for fuel were once the bodies of things that grew in sunlight, living things. Living things exist everywhere on Earth. What part do they play in the story of energy? To begin with, living plants and living animals are very different from the non-living things we've seen. living things begin small. They grow and reproduce. And they move. What great amounts of energy are used by living things. This energy, like almost all energy on Earth, has come from the sun. But obviously, energy affects living things differently from the ways it affects things that are not alive. How do living things use the sun's energy? The answer is that there is one important link between the sun and living things. That link is green plants. Green plants change the sun's energy to the energy of life. Photosynthesis is the process by which the sun's energy is changed. It takes place in the leaves of plants, in cells containing chlorophyll, a green material. In many plants, chlorophyll is in tiny structures, chloroplasts. They function like this. A chloroplast takes in water, carbon dioxide from the air, and energy from the sun. From these materials, the chloroplast produces sugar, with stored-up chemical energy that may be used as food by the plant. How exactly does a chloroplast change the sun's energy to chemical energy? First, sunlight strikes small structures known as grana. These transfer the energy of sunlight to a chemical compound, ATP, an abbreviation for adenosine triphosphate. ATP acts as a sort of storage battery. It releases energy which acts on the water and carbon dioxide that were taken in by the plant cell. It causes the water to break down into atoms of hydrogen and oxygen, and the carbon dioxide to break down into atoms of carbon and oxygen. Some of the oxygen is released into the air, but the rest combines with hydrogen and carbon. This goes on with these and other similar atoms. Finally, we have a large group of atoms that makes up a molecule of sugar, a basic food. Now, the energy is contained by the sugar molecule in the chemical bonds that hold the atoms together. And even more energy may be stored in more chemical bonds as plants transform simple sugars to more complex food molecules. Foods are used by green plants as they grow, as they flower, and as they reproduce. But more important, green plants are the first link in a long series of transfers of energy that make possible the existence of all living things on Earth. The energy in a plant may be transferred to an animal that eats plants, a herbivore. Its energy may in turn be transferred to a meat-eating animal, a carnivore. These transfers may be thought of as a chain, a food chain or an energy chain. And toward its end, we find carnivores that obtain energy by eating other carnivores. As you know, human beings are partly carnivorous. We eat meat. Like carnivores, we use a great deal of energy for movement. We might say that the way energy is released in our bodies is similar to the way in which energy is released by a fire. Of course, there's an important difference between a living thing and a fire. Living things use a great deal of energy, yet they remain relatively cool. Why do living things have such low temperatures? The answer lies within the body, in cells. Green plant cells convert the sun's energy to food, and all living cells carry on the reverse of this process. They convert food to energy. This conversion takes place in tiny structures inside a cell, mitochondria. Into a mitochondrion goes food, say the molecule of sugar we have seen. The chemical bonds, that is, the energy holding the various atoms together, are broken. The chemical elements are released, forming water and carbon dioxide, waste products. The energy that once connected them is now stored in the chemistry of ATP, like the ATP that acted during photosynthesis. Having picked up energy during photosynthesis, this ATP will release energy when muscles and nerves operate. Some of this energy is given off as heat. For example, as food is oxidized in the human body, the heat that's given off raises the body temperature to 98 6/10 degrees Fahrenheit. This is a great deal lower than the temperature of a fire. As wood is oxidized, its temperature is raised to about 500 degrees Fahrenheit. Why does the energy reaction occur in a living thing at a lower temperature than in a non-living thing? The reason is, in living cells, in mitochondria, food is oxidized not by heat alone, but by a combination of heat and the action of chemicals known as enzymes. Enzymes speed up reactions, like the breaking of chemical bonds. But the enzymes themselves do not take part in the reactions. They are catalysts. Enzymes act only in living things. But living things do create some heat energy as they use food, and this accounts for their body temperatures. Mammals and birds have very constant body temperatures. They release heat at steady rates. All other animals have more variable temperatures. They tend to release more heat when they're active, less when they're at rest. Plants in the temperate zone produce greater amounts of heat in the summer, less in the winter. This heat, this energy, leaves the Earth and passes off into space. And most of the energy on our planet would be quickly dissipated in this way if it were not for the sun, constantly renewing our supply of energy while living things continue to exist on Earth.